I wanted to do a bit deeper dive on multilingual and why multilingual semantic search is so much cooler than lexical search. First of all, it gives you actually useful search results, but also in terms of development, it's so much easier. It's like 10 times, 100 times easier to do multilingual semantic search than multilingual lexical search. So first mentioned, as mentioned, lexical search is terrible. Sadly, everywhere you find lexical search. So if you go on Wikipedia, which is an amazing website, really big, really popular, but still search function on Wikipedia is terrible. So if I search for what is the capital of the United States on Wikipedia, first entry is about capital punishment in the United States because it contains the word capital, the United States is, the States is. So on a lexical level, as Lewis said, it's great. But from a user perspective, it's totally disappointing. So in fact, Washington, D.C. is not retrieved on the first site, so it's not among the top 20 results. And you have to click through to actually find the right page you're looking for. And if you don't know that Washington, D.C. is the capital of the United States, how would you know which article you should read to get this information? Probably you don't want to read about capital punishment if you search for this, but yeah, how do you find it then? And what's even worse than lexical search is multilingual lexical search. It's like one of the most painful things you can develop as an engineer because the process really, really challenging. So in English, so how does lexical search work? In English, you take the English text, you tokenize it on white spaces, you look at like all the spaces, and then you separate this into like 3 tokens, multilingual, lexical, and search. Then to deal with like plurals, you apply a stemmer. So you reduce it to like some word stem. And because lexical search has issues with stop words like is, the, and so on, you remove stop words. The issue is that tokenization on white spaces works for English, but it does not work for Chinese. So if you have a Chinese text, you cannot tokenize on white spaces. Also, stemming in other languages is like really different, and stop words in Chinese are completely different than stop words in English. So your actual architecture looks a lot more like this. So you have a document, you run some language identification where you try to identify, is it English, is it Spanish, is it Chinese? And then for each language, you have like an individual pipeline where you first tokenize. So you have some tokenizer for English, some tokenizer for Spanish, some tokenizer for Chinese. Then you need to stem it to reduce, like remove plurals and endings, like exciting to remove the ending. And then you have to run like some stop words and you have to pipe it to like individual indices. So you have an index with all your English documents, you have an index in your, for example, Elasticsearch with all your Spanish documents and an index for all the Chinese documents. And the more and more languages you have, if you have like 10, 20, 100 languages on your platform, in your system, you have like hundreds of these pipelines which you all need to take care of and manage. And then at query time, if someone enters a query, you again have to do like language identification, and you have to know, okay, is it an English query? I have to search the English index. Or is it a Chinese query, and I have to search the Chinese index? And language identification on a query sometimes might appear to be easy, but it's actually like really, really tough. So for example, there's some movies in German, so American movies where the title has been translated to German, but actually they did not translate it to like a German title, but like to another English title. So for this English title, you would actually want to search in the German index because that's the English title for in Germany for German movie. And so you have like all these types of problems that you do not really know what's the language of the query. Semantic search solves this. It makes it a lot easier and also makes it the search results much better. So first on the quality, if you ask the same question, what's the capital of the United States, with semantic search on Wikipedia, first entry is about Washington, D.C. is the capital of the United States. So that's first you have like perfect search results. So you have perfect search results here. So how does it work? So Lewis already covered it. You have these vector spaces where you encode all the documents, and then you encode the query, and you find the nearest neighbor of these queries. How does it work a bit more in detail? So what you have like these queries and documents which you send to a transformer network like BERT. You do some pooling operation to give you a vector. And then you use some combination, some distance measure like cosine similarity, dot product, or so on to get a score. And in multilingual search, the nice thing is that you can map things independent of the language to the same point in the vector space, similar to what Lewis showed. And this makes the multilingual semantic search architecture so much easier. So you take the document query, you pass it to an embedding model, you get some vector, you get the vector in the vector database. That's all you need to do. It works for 100 and more languages. Doesn't matter if you pipe in like a Chinese text, French text, German text, Arabic text, Russian text. You don't have to care about what's the language. You don't have to do any tokenization. You don't have to do any stemming. Don't have to know what are stop words in China. You don't have like all these independent indices. You can pipe anything completely mixed in the same database and you can search on it. And what's even more crazy for me is cross-lingual search. So because everything is a vector, you can search across languages. So you can take this Arabic text, which I'm sadly not able to read, but it's in Arabic, the question, what's the capital of the United States? If you search with keyword search like Elasticsearch on the English Wikipedia, obviously you do not find any entries. However, if you do this and you search with this with semantic search, you get the first entry about Washington, D.C. is the capital of the United States. If your document collection contains Chinese documents or French documents or Russian documents about Washington, D.C., they will also be shown there. So independent of the language, you can find the relevant information. As Lewis said, search in large vector spaces can become computationally expensive. So here we see the query, and for us human, it's kind of easy and straightforward to say, okay, this is like the closest document, so that's what I want to put at the first top. But for computers, it's kind of challenging to really say from all these blue dots which one is the closest to the query. And here you can apply different approaches. First, most simple approach is brute force. So basically, for every document, you compare the distance or similarity to the query, and then you sort them in a like decreasing order, like highest distance to lowest distance, and say, okay, these are the top five documents with the lowest distance or highest similarity to the query. Challenge here is, of course, query time grows linear with the number of vectors. So if you have like 1,000,000 vectors, it takes quite some time to find like these closest points. But if you have like 10,000 to 100,000, maybe sometimes like 1,000,000 vectors, it's still doable to use brute force. So as soon or as long as you don't scale to like crazy large quantities of vectors, brute force is still the way to go. Second option is to call IVF. Here the idea is you run clustering on the vector space. So you take all these vectors you have, you cluster them into cells, and then at query time you put the query into it, you check which cluster cell is the query, and then you look at the neighboring clusters and in the cluster itself to find the closest embeddings for this query. Third technology is HNSW, which is one of the most popular architectures, which is like a hierarchical graph. So in the first level, in the top level, you put only really few embeddings, and you have like really long distances between the embeddings. And then at the query time, you first check in the first level of the query at the start point, what's like the closest neighbor. And then you propagate to the next level. Here you pre-computed all the closest neighbors, and you can then navigate to like or check the neighbors of every point to see if they are closer to the start point. And then once you have found the closest point in this level that's closest to the query, to a starting point, you go to the next level and next level. So in the top level, you have like really sparse vectors and you do big jumps. And the deeper you go in the graph, the more fine-grained the search gets. Luckily, you don't have to take care about this and implement this yourself. So for small data sets up to like 100,000 embeddings, use brute force with PyTorch or TensorFlow or NumPy. This is like a totally perfect solution, especially for a hackathon. If your data sets gets larger and larger, like 100,000 or a million or even more, there are like different libraries you can use, like Phase and HNSW implementing these methods. I can highly recommend to use HNSW, it's really nice. There are different open source vector databases like Milvus, Qdra, and VV8 that are easy to spin up and to use. There are managed solutions like Pinecone and also VV8, Milvus, Qdra, where you don't have to take care of the servers and where they run it on their server themselves. Interesting aspect in multilingual search is language bias. So language bias defines the preference of a certain language combination. So for example, if I search in Arabic, what's the capital of the United States? What languages should the results have? Do I prefer like Arabic results over other results? Do I prefer Arabic results over English results or Chinese results? What if there's a result in a different language that's better, but it's a different language? Should it be like higher in the rank or should it be lower in the rank? And this is like kind of like the language bias. So how much do I prefer my own language, the language of the query, compared to other languages? And depending on the model, you can have like a stronger language bias or weaker language bias. So for example, in the top left, we see a model with a really strong language bias where we have all Russian text in the left part of the vector space and English text in the right part of the vector space. While at the top down, we see a model without a language bias where the text is like heavily mixed between the two languages. And there's a question, is language bias in an embedding model, is it good or bad? And sadly, there's no good answer for that. So let's say you have a model with language bias. So if you search in Arabic, it will find documents of the same language in Arabic, for example, higher just because it's also in Arabic. But there might be better hits or answers in other languages. So maybe you're bilingual and there's another hit in English that's so much better for your search query. Sadly, because it's another language, it's ranked lower. So you could say, yeah, you want to have a model without language bias. However, if you have a model without language bias, which totally ignores the language of the query, you can get the following behavior of the model. So for example, you search for the word wedding, and you do it like in an image search setup, and you find like a picture like this, like a woman in a white dress and a man in a black suit, white skin, like the typical American, Western European picture of a wedding. If you search for wedding in Hindi, and the model does not know about the language, so it does not have like any bias in terms of the language. So here the Hindi word for wedding and the English word for wedding, it represents the same vector, and so it will fetch the same picture. So if you search in Hindi for wedding, you get the same picture. Even such, probably if you search in Hindi, you're more interested in wedding pictures from India. So how does a typical Indian wedding look like, which is not like a picture like this. Similar with things like who's the president. So if you ask this, you might want to have like know about the US president. However, if you ask in French, who's qui est le président? So if you ask in French, who's the president, you might be more interested in the French president and not in the US American president. So language filtering, that's a point probably Amr is going to talk about that. Users have preference for certain languages. So for example, I can understand German and English. If I search something, give me any results in German and English, I'm totally fine and happy to read it. But if you show me results in Chinese, sadly not really able to read it. Sadly, machine translation in Chinese is not perfect yet. So one option, if you have like a really mixed language corpus where you have like, let's say you take all Wikipedia, or you have like articles from Wikipedia across many languages. So one way how you can fix these preferences is you can run language identification on the documents. And then in the VectorDB, you can add like a language tag. Say this is from the English Wikipedia, that's from the German Wikipedia, that's from the French Wikipedia. And then you can filter queries. You say, okay, this is my query. Show me only results in German and English, or show me results in Arabic and Chinese, or show me only results in French. So here you can do filtering based on the language preference you have for search results. And Amara will show more details in the next talk. So the Cohere multilingual embedding model can be accessed quite easily. So first you sign up with our website, you get an API key. So you post your API key here. Then you can define your text as mentioned, can be any language. The model supports more than 100 languages, so it will be tough to find a language that is not supported. You call co-embed, you say the model is multilingual, and then you get your embeddings. One important aspect which is confusing with embeddings, always confusing, here you have to use dot product if you compare two vectors. Don't use cosine similarity. So which metric to use always depends a bit on the model. Sometimes you have to use dot product, sometimes you have to use cosine similarity. Sometimes it doesn't matter and you can use both. But if you use the wrong metric to compare embeddings, performance extremely suffers. So if you use the multilingual model with cosine similarity, you will get really bad search results. And if you just do a switch and use dot product, which is also the more efficient method to compare vectors, you get way better results. So just to keep this in mind, if you follow some tutorials sadly show how to use cosine similarity. So really keep this in mind. Make sure you use dot product. If you have questions on this during the hackathon, reach out, ask on Discord, is this the right metric to compare to embeddings?